Greetings people, this is the first issue of the Intoxication calculus, and the topic of today's discussion will be limits. Usually the study of limits marks the initiation into the world of calculus, where students are no longer able to come back into the simple and fancy world of pre-calculus. However, even for the pre-calculus students, they have on the intuitive level this idea of limits, which is intrinsic to everyone who had long boring review periods when there was nothing to do but just to rape your calculator. Yes, just imagine the situation where you have nothing to do, your phone is very far from you, so you can't use it, and that's why the only thing that you have in vicinity is calculator. So what would you do? You would most likely just plug in some random numbers into calculator and try to do some things which are usually not allowed to do with calculator. Of course, this video shows an extreme version, but still you get the idea. So one of the strange things that you could do with calculator would be to add 1 plus 2, and after that 1.0.1 to 2, and then you add 1.001 to 2. And so you do the same thing with 0.9, 0.99 and so on. Of course you could just add simply 2 plus 1 to get the answer 3, but you feel on some subconscious level this pleasure from avoiding the direct number 1 and trying to approximate it as close as possible. So plugging in values which are ridiculously close to the intended value, this is an example of tedious calculator rape that you will have to do a lot of times in your study of limit. By the way, here is the limit as it is. The function itself is simply rewritten in the part which is designated with f of x. The value of c is replacing the value that you are not inputting directly, but you are always creeping around this value. And finally, the l is the intended value that would be provided by this function if you were constantly approximating your values to this specified value of c. This looks even more clear when you look at it graphically. When you look at these three functions, limit will exist in all cases, whether it's a random point on the upper left function, or it's the point where there is a hole on the upper right function, or it's the central function where you have a hole but a value which is completely different. However, in all those cases the limit will be the same, because not the value of the function matters, but rather the value which is constantly approached by the two sides of the graph matters. If this sounds confusing, look at this function for example. In this case, even though the value at 1 does not exist, the limit as x approaches 1 actually exists, because even though there is discontinuity and a hole on the function, the limit still exists because the value can't be infinitely approaching this hole. Yes, here's the graph of the function, and as you can see, the limit exists for all points of the function. The significance of limit is that you never have been so close to something extremely forbidden in mathematics, which is dividing by 0. You've been always told that horrible things happen when you divide by 0, so here's the consequence of someone dividing by 0 in Japan. That's someone divided by 0 while being on Zeppelin. And finally, in Soviet Ukraine, you don't divide functions by 0, because functions divide you by 0. Moreover, the recent scientific investigations showed that in the Garden of Eden, the serpent provided Adam and Eve not with the forbidden fruit, but rather with a calculator where they were offered to divide 666 by 0, which resulted in eternal condemnation of humankind. But in limits you disregard the holes of the functions, and you can actually find specific values of limit even though there is a hole. In other words, you are allowed to do forbidden things in calculus. The whole concept of evaluating limit at the hole where there is discontinuity is like attending a peep show where you just creep and approximate this abyss of forbidden. But calculus is not omnipotent. In certain cases you will have situations where limit does not exist. For example, this tricky trigonometric function. It is impossible to evaluate the value of limit at 0 because the function oscillates furiously without the ability to determine whether it approaches 0, 1 or something in between 0, 1 and -1. Or consider a more trivial example where the function is defined by two equations with certain conditions, and the graph itself looks like it's not only broken in one whole, but the two sides of the graph do not actually match each other. Even if you come up with additional condition that will give a value for the point at 1, this function will still have a limit that does not exist as x approaches 1. The fundamental rule in this case will be that the right-hand limit has to equal the left-hand limit. The left-hand side limit is designated by the superscript of negative sign, and it shows the value that function approaches from the side of negative infinity, and the same idea applies to the right-hand side limit. So if you are, for example, a left-hand side limit of the function and you come to a meeting or a date and you realize that you are ditched, most likely that will mean that there is no limit happening, and it either means that the right-hand side limit is approaching a different location or it doesn't even exist at all. In case when right-hand side and left-hand side limit arrive at the same place and the same time to the same meeting, in this case the limit will exist, even though there may be a hole and discontinuity in their social communication. So obviously without examples, math is useless. Let's say they provide you with the function and they just ask you to determine the specific values of limits. So the first case is pretty simple, nothing unusual. Limits from the right side and the left side are the same, it all approaches 2. Nothing special, no discontinuity. For limit as x approaches 3, it does not exist because it violates the rule of left-hand side and right-hand side limits. But the limit from the left side actually exists because the function approaches the value of 1.5. Same concept applies to the right-hand side limit, where the function actually approaches the value of 4. So in this case, the limit will still exist. And for the last one, just look at the point 3.3, that's the value of function at point 3. By the way, this function looks like two sperm cells approaching a very, very small egg cell, even though the egg cell is supposed to be much bigger, like that. Anyway, that's biology, not math. So for this one, you can actually abuse your calculator and find some results, but I can tell you that when the function approaches 0 from the negative side, from the left side, which means that the x in this case will approach negative infinity because it comes from the negative side. So it means that the 2 to the power of negative infinity will be pretty much close to 0 or nothing, and the denominator will be close to 1. And the result will be obviously that the limit from the left side will approach 1. However, if you look at the positive side of the limit, in this case 1 over x will approach the positive infinity, and the denominator will become infinitely large, which will eventually result in the value of function which will be almost nothing. However, considering that the left hand side limit and right hand side limit are not equal to each other, the limit does not exist overall. So here's the next example where you have to graph a function which will satisfy the following conditions. So right away you can see that at point 3 there is a problem, since the right hand side limit does not equal to the left hand side limit. So the right hand side limit will approach 4, the left hand side limit will approach 2 in this case. That's the gap that you will have, and there won't be a limit at this point. Oh, and also the function is not defined at that point. That's also quite important. The last condition is that as x approaches negative 2, the limit has to be equal to 2 in this case. So for this reason you can just write, you can even have a hole at this point. It doesn't really matter. It doesn't have to be defined at that point, as long as the right hand side and left hand side are equal to each other. And the last thing to consider are the infinite limits. Infinite limits are actually responsible for those vertical asymptotes that appear sometimes on your graphs. Also important to note that even though the left hand side limit and right hand side limits are equal to each other, the limit does not exist at this point, even though it is an case of infinite limits. So you don't write that the limit does not exist. You just write that the limit equals infinity. However, infinity is not something that can actually exist, so it is assumed that this limit does not exist. For infinite limits, you just have to determine whether it will be positive infinity or negative infinity. In this case, just sub into x1 and you will get the numerator that it will be positive. For the denominator, it will be, then if you sub 1 into your denominator, you have 0, which means that overall it will be approaching positive infinity because numerator is positive and the denominator is approaching 0. However, for the second one, the numerator will approach a negative value. It will approach -1, while the denominator will approach 0, so it will be negative infinity overall. Obviously, infinity is not something numerical, so having left-hand side limit and right-hand side limit meeting at infinity is like saying that people will meet either somewhere here or somewhere here, which is comparable to non-existent place. And finally, it is important to introduce you to the classic limit joke which encounters every calculus student on their entrance to the world of limits. A brief search on the internet revealed that there are 2 versions of this joke, and actually both of those versions are unacceptable because they are sexist and they pick on specific sex. That's why it is important to make this joke politically correct and appropriate. So here it is.
Они говорят, где же это видано, чтоб человек проживал непрописанный в Москве.
That's it for today. Ending on this optimistic note of graphic violence with graphic calculators, we conclude this first video on limits, and our next video will be also on limits, including the rules of limits and other things which might be important for your calculus study. Anyway, stay tuned with the Intoxication.